Today we begin studying Earth-Sun relationships. We're going to be observing how the Earth's movements around the Sun and the Earth's own motions influence all the topics in this particular unit. So here we see the Earth's position at different locations as it orbits in one calendar year. Orbits the Sun, that is. So the Earth is moving. When we talk about rotation, the Earth rotates around an internal axis. This leads to day and night. The side facing the Sun is daylight. In a way, it would be nighttime. A revolution. The Earth revolves around the Sun. This is an external axis. Because the Earth has an axial tilt of 23.5 degrees, different locations of Earth receive different amounts of direct sunlight. So here we can look at the axial tilt as the same 23.5 degrees as the Earth is located in different positions throughout a calendar year. So I can start looking at this a little differently. I can just start on one of the sides. I'll start over here. Because the northern hemisphere, or the Tropic of Cancer, is receiving direct or 90 degree, the highest point, it's receiving the most direct sunlight. So therefore the northern hemisphere as a result experiences summer. And if I look at the 6 months later, or halfway through its orbit, where the southern hemisphere is receiving the most direct sunlight, the northern hemisphere is in winter. So seasons and hemispheres, northern and southern, are flipped or reversed. When southern hemisphere is experiencing summer, the northern hemisphere is experiencing winter. And I can see this because the northern hemisphere is receiving the least direct sunlight and for a low amount of time, or the shortest amount of time. And the positions from winter to summer is my spring equinox. This is where the equator is receiving the most direct sunlight, and the hemispheres are receiving 12 hours of daylight and 12 hours of darkness. And this would be my autumnal or fall equinox, where it's 12 hours of daylight and 12 hours of darkness as well. So Earth-Sun characteristics. The Earth is located, on average, 93 million miles, or 150 million kilometers from the Sun. The EarthSun Distance is referred to as 1 AU, or 1 astronomical unit. This value changes due to the Earth's elliptical orbit around it. Right? Around the Sun, the Earth moves in an elliptical orbit, meaning the radius is not the same. The radius changes. So here, when I look at the locations here, I'll look at our solstice. In December, we're actually closer to the Sun. But because our axial tilt is the way it is, we're receiving less direct sunlight. We're also receiving less direct sunlight for less amount of sunlight hours. So we have longer nights and shorter days. Whereas on June 21st, our summer solstice, we're receiving more direct sunlight for longer periods of time, or a greater duration of the day. But I want to make sure we have a chance to go through this. Seasons are not based upon the distance from the Sun. Instead, seasons are the result of the directness of sunlight an area receives. So here I can see this. This would be an example of an equinox, where the direct sunlight is striking the equator at 90 degrees. The further I get from the equator, the amount of sunlight measured in watts per unit area, the amount of sunlight, the energy, is dispersed over a greater amount of area. So therefore, if you look at this red area here, that same amount of sunlight at the equator that's hitting this small area is spread out over a much larger area. So therefore, it's receiving less direct sunlight, and that amount of sunlight is spread out over a greater area. So energy from the sunlight is not spread evenly over the Earth. One hemisphere is always dark, right? That's darkness, nighttime, and receiving no solar radiation at all. On the daylight side, only the point directly under the Sun receives the full intensity solar radiation. From the equator to the poles, the Sun's rays meet Earth at smaller and smaller angles, and the light gets spread over larger surface areas. And these are the red lines in this picture here. So here I can view this again. If I look at this picture, I see the Tropic of Cancer is receiving sunlight at 90-degree angle. This tells me that this is June 21st, or a summer solstice. In this case, the more the direct sunlight, the more power, which we measure in watts, an area receives. In the picture closer to the sunlight angle of 90 degrees, this is going to receive more energy per unit area. So if I look at this picture here, where the sunlight is coming at a 73-degree angle, this amount of total energy in these 5 arrows, or these 5 rays, are distributed amongst 1.04 meters squared of area. Whereas this low incidence angle of 26 degrees, that same amount of sunlight energy, denoted by these 5 incoming rays, is spread out over 2.24 meters squared. In other words, this is getting much more direct sunlight. This sunlight is getting, well, that heat energy distributed over a greater area. So when I look here at this picture, we can study the solstices and equinoxes at the same time. Solstices, there are two solstices in our local area, December 21st and June 21st. And these are where the Earth receives more or less sunlight during daylight hours at different angles of insolation. On June 21st, our summer solstice, the northern hemisphere is tilted towards the sun. Well, this just happens to be darkness. But the northern hemisphere is receiving the most and the greatest sunlight at 23.5 degrees. So the Tropic of Cancer is receiving sunlight at its zenith. The sun's zenith, the highest point in the sky, is 90 degrees directly overhead. Where in the winter solstice, the Tropic of Capricorn is receiving the most direct sunlight, or the zenith is 90 degrees overhead. Where the sun, the northern hemisphere, is receiving a lower incidence angle of sunlight. So it's distributed over a greater amount of area. So we can actually determine the sunlight, the noon sun, which we can also call the zenith. So I subtract if it's on the top of the analemma chart, meaning northern hemisphere, and I add if it's on the bottom or in the southern hemisphere. So if I look at this analemma chart, this line right here is dividing northern and southern hemispheres. So this 0 degrees is the equator. So seasonal changes in insolation occur at different angles. At any given time, the intensity of insolation is at a maximum at the latitude where the angle of incidence is 90 degrees, or closest to 90 degrees. The latitude of maximum intensity of insolation shifts in the northern hemisphere with the seasons between June 21st to the minimum intensity on December 21st. So on June 21st, it's the most directly above in the northern hemisphere. On December 21st, it is located on the southern hemisphere, or directly over the Tropic of Capricorn, and the northern hemisphere is receiving the lowest amount of, or the minimum intensity. So if I look at that based on the binder, the practice problems in the binder, the noon sun angle, let's see here. So in Chicago, so 42 degrees north tells me this is showing Chicago. So if I solve for the noon sun angle, I can take noon sun angle equals 90 degrees minus the latitude, right? Latitude, I'm talking you through this equation here. Noon sun angle equals 90 degrees minus the latitude plus or minus declination. You need to make sure we know what we're doing with plus, if we're adding or subtracting the declination. So I find my declination here. I find the date, August 10th. I find my declination on August 10th here. August 10th is going to be located right here. I find this over here, and it's 16 degrees. So 16 degrees. It's on the same hemisphere as Chicago, so I subtract them. Subtract if same. So 42 north minus 16 degrees north gives me a value of, what is that, 26. I take 90 minus 26, and I get a value of 64 degrees. On September 21st, this is actually at the equator. Where are we at? Right here, so roughly September 21st, 0. 42 minus 21 is 21. Let's see here, 42, yeah. In this case here, let's see, 21. Oh, 21 is my date. 0 degrees. 42 minus 0 is 0. 42 minus 0 is 42. 90 minus 42 gives me 48 degrees. So the zenith would be 48 degrees. And on June 21st, if I can find June 21st here, let's see, June 21st. June 21st is up here. I follow it over here. I get roughly 23.5 degrees. 42 north is my latitude, minus, because it's on the same hemisphere, 23.5. I get 18.5. 90 minus 18.5 gives me a value of 71.5. And I do the same thing, but notice I divided the southern hemisphere part of the analemma for you over here, and I do the same thing. And I'm only going to do one over here. October 15th is my date. So October 15th I find, let's see here, October is going to be right here. Here's October. October 15th is right here. Bingo. Follow it over here. I find my declination of 8 degrees. So 42 north, it's on the opposite hemisphere, so I add them. 42 plus 8 is 50. 90 minus 50 shows me that it's 40 degrees. So the noon sun angle on October 15th is 40 degrees. And that's 40 degrees above the horizon. And that would be the sun's zenith. So what is the noon sun angle? So I can use this picture in the binder to kind of help make sense of it again. At 40 degrees north on December 22nd, I want to find that the location of 90 degrees sun is at 23 degrees south, 23.5 degrees south. So step one to calculate this, the distance in degrees, I take 23.5 plus, this is my declination, plus my latitude of 40 degrees north, I get 63.5. I take my equation, 90 degrees minus 63.5, which is my latitude. In this case, it'd be plus my declination of 63.5, and I find that the noon sun angle at 40 degrees north on December 22nd is 26.5 degrees. So here's where I have the effects of latitude. Essentially, we're looking at daily maximum and minimum temperatures, and I want to make sure that we have a chance to do this properly and correctly. So if I look here, here's an equinox, here's my summer solstice, and here's my winter solstice. So I'm putting it all together. But I want to make sure we're clear that maximum and minimum temperatures, the hottest part of days are mid-afternoon, not at the solar noon when the sun is the highest in the sky or at the zenith. Insolation may be the greatest at solar noon, but the temperatures are at a maximum after the Earth has had many hours to fully absorb as much incoming solar radiation as possible to convert it into heat, right? The Earth re-radiates sunlight as thermal or infrared heat. The coolest temperatures are typically found just before sunrise because the Earth has had a maximum amount of time to re-radiate that infrared or that heat energy back into space or the atmosphere around it. So it's the coolest point. And heat is lost until sunrise and insolation begins again. So much like that day and night temperature highs and lows, seasonal variations occur much like that daily thermal lag time of that of temperature up here. The warmest or highest temperatures do not correspond to the greatest sun angle. Instead, there is a thermal lag time seasonally too. And here's what you should have done in class. You were provided we calculated the noon sun angle in Chicago on these dates. If I graph these, the date and the temperature, if I graph them in one color, and then I graph the average temperatures on these particular dates that were provided in the binder, you'll see that the graphs are a little bit different, and here's why. We're just graphing the thermal lag time on the graph where the sun angle is the greatest. Chicago does not experience its greatest temperatures. Instead, it takes a while for the land to really fully absorb that incoming solar radiation, so it takes a while for the heat for it to completely heat up, as we see in this graph. In this picture, this difference right here is technically my thermal lag time. And there you have it.